Hello, today we will start a new chapter. It is called elasticity or mechanical properties of solids. So let's start. Mechanical properties of solids. In this chapter, we will see stress, strain, modulus of elasticity, modulus of elasticity. In that we will see Youngs modulus, bulk modulus, sharing modulus, and the Poisson's ratio. Okay. Now we will see the last is thermal stresses and strains. Okay. Now these are the four. Okay, let's start the chapter by stress. Stress means the force exerted on an area. This is an area. This is the force exerted, or you can say the pressure. So we can write the formula as stress is equal to force upon area, and we know that force upon area is the pressure. Stress is equal to pressure is equal to force upon area. Okay. Now the units of force are Newton and area is meter square. So it is known as Newton per meter square. It is the stress. Now there are types: longitudinal stress, bulk stress, and sharing stress. Longitudinal, two, bulk, three, sharing. Okay, there are same formula. That is force upon area. Okay, it is length, longitudinal, like this. This is understood, and we will longer this. The length, and it is volume, bulk, and it is breadth. Or you can say, you can simply written. Now we will see the strain. Strain. The main important basic formula of strain is change in configuration that means initial constant, or it is the final. minus initial. Is how much it is changed from the initial upon initial concentration. It may be either length, breadth, area, volume, and so on. We can write this for the temperature also in other chapters, but in this we will see for the solids, liquids, and gases. Okay, and it is stress has no unit because the numerator term and denominator term is same, so unitless but dimensionless. Okay, now we will write the types. First copy this. Okay. Types. These are all same. First, longitudinal strain. That means the length is changing. So we can write it as strain is equal to change in length upon original length. Now it is strain is equal to, I will also write this. Now it is length, so we can write it as delta L upon initial length. It is the final formula and it has no units. Less. Okay. Now the second is sharing strain. Okay, sharing strain. First, suppose it is a cube. Okay, and we have elongated this, and it has increased the length x, and the initial length is L. So we can write the strain as x upon L. The simplest one. Now we have completed stress and strain. Now we will see some problems related to the stress and strain. First, copy this. Okay. Now we will see some problems. Okay. First problem is find the greatest length of steel wire that can remain hanged vertically without to the power of 8 Newton per meter square. And the density is 8 into 10 cube kg per meter cube. Okay. Now the weight. Find the greatest length of the steel bar that can remain hanged vertically without breaking. They have given the breaking stress and the density. Now we want to find out the greatest length. That means length. So we know that breaking stress is equal to weight upon area. Because force is also written as weight. Now the formula of the weight is in terms of density is mass into m into g. This is the weight and becomes add a. So it is rho v g upon a. It is mass is written as density into volume. It's equal to rho a L into g upon area. So it is the density, length and g. So you want to find out this length. Okay, this length. Now L is equal to breaking stress breaking stress is equal to rho Lg. So L is equal to breaking stress upon rho g. So breaking stress is equal to 8 into 10 to the power of 8 upon 10 cubed into 10. So it will step 4. So the greatest length is 8 into 10 to the power of 4 meters. So by giving the breaking stress as 8 into 10 to the power of 8 Newton per meter square and the density is 8 into 10. So excuse me, it is 8 into 10 cube. So 8 will cancel and here it is 10 to the power of 4 meters. So by giving the breaking stress and the density we can find out the greatest length. Okay, first copy this. Now we will see the second question. Okay, here is the second question. Now second question. Consider a rod of steel having radius of 8 millimeters and a length of 2 meters. Okay, so the first case is they have given a rod of steel having radius 8 millimeters and length of 2 meters. Now the second case, if a force of 150 kilonewton stretches it along its length. For suppose if 150 kilonewton of force such as its length. That means it elongates. Now find out the stress. Stress and percentage strain in the rod. Percentage strain in the rod. If elongation in length is 7.46 mm. Okay, now we will see the okay, now we will see first we will write what they have given in the question. Now answer. First, radius r is equal to 8 millimeters, 8 mm, and we want to convert into the meters. 8 into 10 to the power of minus 3 meters. And if we will write area now only. So area is equal to pi r square. Pi r square. And the area is the value of pi is 3.14 into 8. 8 into 8, 64 into 10 to the power of minus 6 meters square. This is the area. Okay. Now they have given the length. L is equal to 2 meters. And they have given the force, that is 150 kilonewtons. Okay. First we will solve this stress. The formula of the stress is equal to force upon area. Force is 150 into 10 cubed upon 3.14 into 64 into 10 to the power of minus 6. If you solve this, you will get the answer. Now, next, they have given the percentage strain. We want to, excuse me, this elongation of length. So, delta L. Delta L is equal to 7.46 into 10 to the power of minus 3 meters. Now, we want to find out the percentage strain. So, percentage strain is equal to delta L upon L into 100. This percentage, so we want to multiply into 100. So, 7.46 into 10 to the power of minus 3 upon 2 into 100. If you solve this, you will get the strain, percentage strain. And if you solve this, you will get the percentage. So, it is the test. So, we have completed our second question. So, please copy this. Okay. Now, we will see a pulley problem. Now, third question. Two blocks of masses 2 kg and 3 kg are connected going over a smooth pulley as shown in the figure. Now we will draw a diagram showing a pulley two kg and 3 kg with the pulley. Now they have given the braking stress. Braking stress is equal to 2 into 10 to the power of 9 Newton per meter square. Okay. Now, what would be the minimum radius of the wire used if it not used to brake? If it is not to brake. Okay, now we will solve this. First we will discuss the question. There are two blocks of mass 2 kg and 3 kg are connected by a metal wire. This is the metal wire over a smooth pulley as shown in the figure. Now in the figure showing the two masses 2 kg and 3 kg, and the braking stress in the of the wire is 10 to the power of 9 meter square. What would be the minimum radius of the wire? It is OF of the wire if it is not to break. Now we will find out tension. From the Newton's laws of motion chapter, the tension value is T is equal to 2 m1 m2 into G upon m1 plus m2. Okay, it is the value. Now we will write 2 into 2 into 3 into 2 upon 2 plus 3 5. Okay, 2 into 2 4, 4 into 3 12. Here it is 10. 120 by 5. So 24. Okay, 24. They have given the acceleration? No. Okay, wait. And the braking stress is braking stress. 1 minute. We can write it as stress. Stress is equal to 2 into 10 power of 9. Now 2 into 10 to the power of 9 is equal to 24 upon area. Now area is equal to pi r square. By solving this equation, you can get the area. So area is equal to 24 upon 2 into 10 to the power of 9, and R is equal to 24 upon pi into 2 into 10 to the power of 9. Okay, the radius will come from this if we solve this equation. Okay, now we have completed the third question. We will discuss the fourth question. Okay guys, this is the last question of the stress and strain. If you got alright, you can solve any question related to the stress and strain. Okay, question number 4. Consider a solid block of cube. This solid cube which is subjected to a pressure. They have given a pressure of P. I am taking example. Due to this pressure, the cube is shortened by n percentage. Find out the volumetric strain of the cube. Okay, this is a simple one. You can solve. They are given a cube, solid cube. So it has delta V by V, volume, solid. So delta V by V, we want to find out. Okay, and this is shortened by n percentage. So now we have delta L by L is equal to n by 100. Is n. Okay, delta L by L is equal to n by 100. Here 100 by n percentage. Upwards and downward cell both cancel. Now delta V by V is equal to delta L by L plus delta B, that is breadth, plus delta H upon H. Here they have showing the cube. So delta L by L plus delta L by L plus delta L by L. From the first chapter, that is 3 into delta L by L. This delta V by V. From this, we can get the answer as delta V upon V is equal to 3L upon 100. For suppose in the question they have given by 2% or 3%. So 3 into 2 by 100. 3 into 3 upon 100. So this is the simple one. Simple technique. There is a big technique. You can avoid the technique. So this is the simple one. So you can solve by this technique easily this question. So delta pressure, they are given pressure, they are applying a pressure of P on a solid cube, and the solid cube shortened by n percentage, and I want to find out the volumetric strain. With delta L by delta V by V, they have given delta L by L. So delta V from this It is only for cube. If they are given for square, we can ignore this term. So this term will be ignored. And here it will become 2 into delta L by L is equal to 2 into delta L by L. For square here. Square. Square. Okay, square. Okay, this is the square first. Okay, now we have completed the questions and the concept related to the stress and strain. Now we will see the modulus of elasticity. First we will see only the Young's modulus in this session. In the next sessions we will see the bulk modulus and so on. First copy this. Okay guys, now let's see the Young's modulus. Before going to the Young's modulus, we will see the Hooke's law and what it states. Looks like so simple. You can learn in a few seconds. Okay? Hooke's law. Hooke's law states that for a small deformation, means for a compression, for say this is, if we compress the wall, change in configuration by original configuration and the pressure upon area or proportionality. That means for smaller deformations, stress is proportional to strain. Okay? Here strain means force upon area is proportional to delta L upon L. From this, FL is proportional to A into delta L. This is also case we can write in the examination. They can ask for this also. Here the proportionality constant. Here it is the proportionality constant that is known as modulus of elasticity. Modulus of elasticity. Okay. Now this modulus of elasticity depends upon nature of substance. That means how the substance is, either it is hard or soft, or it is malleable or ductile, and the temperature. Introduce. Okay, now we will see the independent one. It is stress and strain. Simple. Stress and strain. Now, for stress and strain, it does not depend. For nature of substance, bulk, temperature, it will depend. Now, we will see the Young's modulus of elasticity. First, copy this. Okay, now we will see the Young's modulus of elasticity. Here it may be delta V by V It may be anything, depend upon the case given in the question. Youngs Modulus of Elasticity. Now, there is a case. A rod of length L. This length. Okay. And of area A. It is undergoing a force. This force. Now it elongates, and the final becomes this delta L. It elongates, and it has a value. So it has force, area, delta L and L. The case is a rod of length and an area A are subjected to a force F, and they are elongated by distance delta L. So we can write that F by A. Before writing F by A, stress is proportional to strain. Here stress means force upon area is proportional to delta L upon L. Here it is replaced by Y. From this we can write the value of Young's modulus as F by A upon delta L upon L. Okay. Now it is become F L upon A into delta L. This is the final one answer. Final answer formula. You can learn. Now we will see what is proportionality and what is inversely proportional. Y is proportional to force and proportional to length. Or we can write for the two y's, y1 and y2 is equal to f1 by f2 into l1 by l2 into, here it is reverse, a2 by a1 into delta l2 upon delta l1. Okay, now we will see for a string y constant. It is denoted by k. Now, okay, it is the elongation. So the value of k is equal to ya upon L. That means we know from the work power energy F is equal to K into delta L. So K is equal to F upon delta L. From this we can write this. Okay. Now we have completed the concept of Young's modulus. Okay, there is some more. F is equal to mg. If they have given mass and gravity in the face of force, and area is equal to pi r square, and L is equal to L, delta L is equal to L. Okay. Now y is equal to mgl upon pi r square into delta L. Okay. Now we have completed concept of Young's modulus. Now we will see the problems. First, copy this. Okay? Before going to the concepts, that means the problems, we will see some important points. Okay? Young's modulus is applied for solids only, but not for liquids and gases. Okay, it is applied for solids only because it has a length, area, and you can apply force. It can change its length. Okay, so that's why it can only applicable for solid only. Now, for rigid bodies, what is the value? Calculate from this. It can't elongate. So, for rigid bodies, delta L by L is 0. So, Y is infinite. So, we can't apply. The Young's modulus is infinite for the rigid bodies. Okay? Y is smaller for ductile substances. Okay, now I have completed the concept completely. Now we will see the problems. We will see the problems, some problems in this session, and we will complete this session. Okay, we will see problems. Okay, if a wire, some basic problem. First problem, if a wire of length, they have given the length of for suppose 2 meters and area of cross section is of, it's of the same length and area of same is stretched. It is stretched. That means force is applied by a force of 4 kilonewton. Then determine the change in length. Now we want to find out the change in length. It is a simple. We can directly apply formula and we solve. And Young's modulus is Young's modulus is 40, or you can say it is 80. 80 into 10 to the power of 9 Newton meters power of minus 2. Okay, we will solve this question. First we will write what we have given. First, length. L is equal to 2 meters. And area. Area is 2 meters square. And the force. F is equal to 4 into 10 cubed Newton. And the Youngs modulus. Y is equal to 80 into 10 to the power of 9 Newton per meter square. And delta L is equal to dash. Now first we will write the formula. Y is equal to F upon A upon delta L upon L. It is equal to Fl upon A into delta L. Now we will write the delta L. Delta L is equal to Fl upon Ay. Okay? Fl upon Ay. Now we will write the values given here. That means 4 into 10 cubed into L. L is 2 upon area. Area is 2 and it is 80 into 10 to the power of 9. Okay? Now here 2 will be cancel and here 1 upon 20. Here it will become 10 to the power of 10. So delta L is equal to 1 by 10. So 1 upon 2, 0.5 into 10 cubed upon 10 to the power of 10. Here it will become 2 into 10 to the power of 1. 1 plus 9, 10. So 10 to the power of minus 7. And delta L is equal to 5 into 10 to the power of minus 8 meters. Okay students, now we have seen first question, the first question in the Youngs modulus. Now we will see the second question. Okay, we will see a different one. Okay. Now we will discuss only a question, single question this now, and we will see the remaining questions in the next session. Okay, the last question is, a cable is replaced by another one of same length. Now they have made our question simple because the length and area are same, but the area is doubled. The diameter is twice. Okay, how will this affect the elongation under a given load? Under a given load, how much, how does this affect the maximum load? Maximum load, it can support without exceeding the elastic limit. Okay? Don't be afraid. This question is so simple. First, we will write the delta y equation. First, I will explain the question. Here, the length and the material are same. So, we can neglect the mass, due to gravity, the elongation, and the finally by the y also. So we can write first the formula is y is equal to mgl upon a into delta L. Okay. Here they have given only the case, that is diameter is twice. Only the diameter. Okay. Now there are two conditions, y1, y2, m1, m2, l1, l2, a1, a2, and delta l1, delta l2. Here we can equate is equal to, and it is not is equal to. So we can write the formula that y1 is equal to y2, or we can write one minute, it is first we will substitute y1 is equal to mgl, okay, mgl upon delta L into, it is d, diameter, so d square, by d square it is initial, and y2 is equal to mgl upon delta L into pi d by 4, d square. Okay. First we will see the case that how this affect on elongation. Okay, we will see the elongation. First I will rub up to this. Here, now y1 is equal to y2. That means mgl upon delta L into pi d square is equal to mgl upon delta L into pi d whole square. Here it is 4. Now we will see that delta L, from this we can cancel out this and d, it is d. Now from this we can see delta L is inverse proportional to d square, because delta L will go upside, d square, that effect is inversely proportional. Delta L is also same. Now the second. How does this affect the maximum load it can support without exceeding the maximum limit? Now it is saying the weight with maximum weight. Now if we drag this to upside, so M maximum load is proportional to D square. So we can say if they have given the diameter effect, the diameter is inversely proportional to delta L, and it is proportional to maximum weight. So we have completed the session 1 of the mechanical properties of fluids with the second question of the Youngs Modulus. In the next session, we will start the third session. Do like, share and subscribe.